So let us start our today's seminar, and our today's speaker is Dmitry Kropotov. Who will give a talk about his and his colleagues' recent research on scalable Gaussian process and the application to machine learning problems.
Okay. In this semester, all the talks in our seminar was about papers that were accepted for NIPS. So this talk opens a series of talks on paper that was rejected from NIPS. So if you miss some details from this work, it doesn't really matter because it's mostly work in progress, and we should do something additional in order to have an acceptance. Okay, we're going to speak about Gaussian process models and some learning procedures within it. So the standard disclaimer when someone starts to talk on Gaussian process, we should say that, well, nowadays we have deep neural nets, and why should we use any Gaussian process models at all? And is it really important to discuss some efficient training procedures within these models? Is it beneficial or not? I think that, at least concerning this task, this talk, it is worth discussing this topic because of at least two things. The first one is that if we trying to construct some family for probability distributions, for some complex probability distribution, for using further in variational inference, for example, what we have? We have a neural net that is perfectly models some nonlinear function, but if we speak about some probability distribution, we take just a normal distribution or something like this, and the mean value produced by a neural net. This is a rather restrictive family of probability distribution, and Gaussian process model, which is a Bayesian model, which produces some distribution at the predictions phase, it could be interpreted as a way to introduce such kind of nonlinear sophisticated probability distribution. That is the first point, and the second point is about Tensor Train decomposition. Tensor Train decomposition is some particular way to work with multidimensional tensor, to store them efficiently, to make some linear algebra operations with them. And to the current moment, we say that this approach were successfully applied in a diverse range of problems. It was not applied only for solving some differential equations and solving mathematical physics problems. It was applied for efficient inference in graphical models, for modeling weights in neural networks. In this work, we're making an inference in particular Bayesian model. So it seems that this approach could be beneficial in many areas, in many problems that you hopefully face with. So, for example, it could be a case that this Tensor Train decomposition would be beneficial not for inference in this particular Gaussian process model, but we can use it for general inference in Bayesian models of more complex kind. So that's the second point. Okay, let's start. For those who are not quite familiar with the Gaussian process framework, I will give a very short introduction on what is Gaussian process first. Well, Gaussian process gives us just a probability distribution over a set of real-valued functions, usually smooth functions. So we have a distribution over a function, can sample function from a distribution, can measure the probability which function is more likely or less likely. And as in standard Gaussian distribution, the Gaussian process is governed by two parameters. First is mean function, which is shown here as a blue curve, and our samples are situated around this blue curve, the mean function. And the second thing is so-called covariance function. That is a sum function of two arguments, of 2 points from our input space. So the function is an object from infinite dimensional space. So how do we actually work with this object on compute in practice? In practice, we usually do the following thing. Let us fix some finite set of points in our input space. In these examples, there are 4 points, x1, x2, and x4. And we consider the values of our function, which is simulated from our Gaussian process model, at these 4 points. So we get some 4 numbers for 1, for 2, for f4. And these 4 numbers form just the 4-dimensional vector, a usual 4-dimensional vector for sampling which we can consider any 4-dimensional distribution. If we speak about Gaussian process, this 4-dimensional distribution is actually a normal distribution with a particular mean vector and covariance matrix. Mean vector consists of the value of mean function at these 4 points. And the covariance matrix, it is a 4x4 matrix, it consists of the value of covariance function for all pairs of these axes. So we have 4 axes, 16 combinations, 4x4 matrix, and have some distribution on this vector f. Certainly, it's not necessary to take this point x at a regular interval. We can take arbitrary points in our input space. It is not necessary to take a 1-dimensional x. We can use any multidimensional input for our Gaussian process model. And also, it is not necessary to take 4 points. We can take any finite number of points, like n points, and consider distribution on n-dimensional vector, which is a Gaussian distribution with parameters which is written here. So that's the way that we usually work with Gaussian, with a function from Gaussian process in practice. The actual appearance of the functions that we simulate from our Gaussian process model is heavily determined by the covariance function that we use. The popular family covariance function is so-called discrete exponential function. It depends just on the difference between 2 points and some parameters theta. And here we have three cases, 3 kinds of exponential covariance function with different theta, and the distribution that we actually get from this function. In the first case, we see that for points that are close to each other, we have a high value of covariance. That is why the samples are smooth from this distribution. But on the large distance, the value is small or near 0. And that is why the function that we actually generate from this GP can oscillate quite fast. So it can be a function which is smooth, but it can oscillate quite fast. On the other extreme, if we take covariance function like this, the function that for large distance between points gives a high value of covariance. Just a second. We get samples which are very, very smooth that can highly oscillate because of this strong dependence between points.
For these images, you should also have a white noise component for the covariance matrix.
Well, yes, it is. These samples, these images are actually taken from trained GP model on regression. It doesn't matter. The mean function could be like this. It can be 0, but the variance would be the same for these 3 cases. Doesn't matter the mean function we use. Okay, so Gaussian processes give us samples of smooth functions. Let's just use them as a regression function for reconstructing non-linear multidimensional regression problem. Here the probabilistic model that we usually use in Gaussian process regression, we introduce f. F is a vector, is the value of Gaussian process at the training points. So if we have n training points, this vector f has the size n, and our probabilistic model, joint distribution of outputs and the value of our Gaussian process, can be split in 2 terms. The first one is the usual data term, which is a product over training objects. And the second term is a prior distribution over our function taken from GP. And we say that it is taken from GP with zero mean function and some covariance function for instance, squared exponential with some parameter sigma. And as for data likelihood term, as it is the simplest case for regression, we can say that our observed sample is just a noisy version of the true regression function. So we put here this likelihood function, that is our model. Then, if we move from regression to classification problem with two classes, we can introduce our model in a similar way as it is done in logistic regression. We say that, again, we restore some regression function in our multidimensional space and interpret the value of this function as some score for an object to belong to the first class, for example. And then introduce some likelihood for the object to belong to the first and to the minus to the second class, as it is done in logistic regression, and easily come to the Gaussian process model for classification with two classes. Okay, what we should change next if we considering classification with many classes? Actually, the same thing that is done in multidimensional logistic, in multi-class logistic regression, multinomial. We need to introduce several Gaussian process, separate Gaussian process for each class. So we have this Gaussian process gives us a score of an object to belong to this particular class, and that is why on the prediction stage, what if we already have a learned set of Gaussian processes, we just take a maximum of all these processes and give an answer. So the probability model is almost the same as it was for two-class classification. The only difference is in likelihood. In likelihood, here we have a set of Gaussian processes, and so we take a softmax here. Okay, now if we move further and consider the structure prediction problem, which is very similar to multi-class classification with a little simplification. Okay, what is structure prediction? Again, we have some inputs and outputs, but now outputs lives in a complex space. It is not just a set of class labels, but some complex set of outputs. For instance, if we consider an instrumentation problem, our object is a picture, or actually it is a feature vector for each pixel in the image. And our answer is a segmentation of the whole image, meaning that we should give a class label for each pixel on the image. So our output set consists of number of labels at the power of number of pixels elements. So it's a huge space of all possible segmentations of a particular image. And so how this structure prediction problem is usually solved? We introduce a score function of the following form. It consists of two terms, so-called unary potentials and pairwise or binary potentials. And in the first sum, there is sum over pixels of an image. And here stay, a score of pixel number p belong to class label yp. So usually people take here a score taken from a classifier which was trained on all the pixels which are interpreted independently. And also there is a term, a binary potential. Using this binary potential, we can model the situation like that for neighboring pixels, we encourage them to have the same class label. Or for some pixels with similar feature vector, with similar colors, we'll also encourage them to have the same class labels. It's easy to do with these binary terms. And then if we have this score for a particular segmentation, a particular image, then in order to make a prediction, we make a maximization with respect to all possible segmentation. So here states combinatorial, actually, optimization problem. And this problem is not easy to solve in general case, and the courses on probability graphical models usually concentrate on different methods for solving optimization problems of this kind. So now, what should we do if we want to solve structured prediction using Gaussian process? Simple. We just use our previous multi-class Gaussian GP model and change the score function here. So now score is not a score for a particular class. Now we have this sum. So we need to introduce again a separate Gaussian process for each class label, as in previous case. And also we need to introduce the Gaussian process for binary potentials, but usually people, in order to reduce somehow the number of parameters that we need to optimize, they introduce only one Gaussian process for binary potential and say that this Gaussian process, the covariance function of this Gaussian process actually doesn't depend on x, on input points. It depends only on y, on class labels, and depends like this. So we have some covariance only in cases when two pairs of classes coincide. It is the same as to say that we have just a normal distribution of class labels, and that's all. With some covariance function that we
What does it mean, normal distribution of class labels? Class labels are discrete variables. So?
No, we have a normal distribution over the potential on each pair of labels, which is the real number.
I still do not understand. Let's try to describe it in more details. So we have a covariance function that depends on two pairs of labels, right?
Yeah.
And it equals to 1 when
these pairs coincide.
Then it's 1 and 0 otherwise.
Yeah.
What does it mean physically?
Well, it is just a way to reduce the number of parameters. Using this way, in general case, we need to introduce a separate Gaussian process for each possible pair of labels.
I understand, yes. But instead of this,
Instead of this, we introduce only one, so it doesn't depend on a particular pair of labels.
but what is even more, it doesn't depend on x's, actually.
And it doesn't depend on axis, yes.
That's a bit strange.
Why? If we want to model just a situation that we put a penalty if two neighboring class labels are different, it's okay with this model. We can easily model, consider this situation.
What would be the distribution of f bin if the labels ypi, yqi are the same? So this
Some
is
value,
some value distributed to according to what distribution? Normal
their
distribution.
joint distribution is normal.
Just standard normal distribution.
Yeah.
And if the labels are different, then.
Again,
But then what's the difference between two cases, when the labels are the same and when they're different? Because there should be some difference in pairwise potential, right?
yes.
Because this is the key essence of CRF segmentation problem. So,
Well, because of this assumption, we don't need to compare pairs of class labels. It's enough for us to consider only one pair, not two pairs.
Very, very stupid question. I don't really understand what is YP. 1 and yp2. What is 1 and 2?
Vector of diagonals.
Well, the covariance function depends on two inputs.
P and Q are different pixels, yes?
P and Q are different pixels, yes.
Yeah, and 1 and 2?
Are different arguments.
We need to establish covariance function between two pairs of labels.
Yeah.
And this is exactly what is done there. So this is, but okay. What would be the analog for unary potential? For unary potential, then you should establish covariance function that depends on pairs of labels. But you do not do that because you simply establish different Gaussian processes for different labels, right?
No.
Why not?
For unary potential,
Right.
we put a separate Gaussian process for each label.
That's exactly what I told.
And this, the covariance function in this Gaussian process depends on axis. It is the same covariance function for all Gaussian processes, but with different parameters. For each class, it has its own parameters.
And what about covariance between different Gaussian processes, which are associated to different unary labels? Is there any covariance, or we treat them just as?
I don't understand what's covariance between different Gaussian processes.
This is exactly what you're defining.
We can
by the-
input only covariance function within one Gaussian process. And we put covariance on inputs to the process.
If we speak formally, we may at least, hypothetically, define covariance between two Gaussian processes if they're defined on the same domain, right? Because those Gaussian processes can be, at least in theory, correlated. The reason I'm asking is that I do not understand. You have
You
two completely different.
mean a function that depends on four variables, two variables for the first process, two variables for the second, and we define a covariance function in this.
Probably I should better write. You have one Gaussian process, another Gaussian process. These are two different Gaussian processes, right? But we may define something like this. In particular point x. Does it make sense? Or we may treat them as completely independent from of each other Gaussian processes.
Okay.
As far as I understood, you treat them as independent. So this is always zero.
Yes.
But for the binary term, the situation is different. Because you're not defining just different Gaussian processes for each pair of labels.
Yes.
Instead, you're defining the same process,
Just one.
just one, which you call f bin, right? At the point, at which point x prime? What is the domain of this Gaussian process?
Either a pair of labels or one label, depending on how you talk.
And what is the domain of these Gaussian processes?
A pair of x and y.
Okay, this is y, this is x. So this for f bin, is there a dependence of x?
No, because that's our way to introduce covariance. It just depends on x.
But if f bin doesn't depend on x, and we have just finite number of
It
y's,
depends only on y's.
but if it depends on y's, this is not a Gaussian process. This is actually a multidimensional Gaussian variable.
Okay, yes, that's what I said at the beginning.
So this is not Gaussian process f bin, right? F bin is simply multidimensional Gaussian random variable.
No, because our domain is finite.
Yes.
That is why
Yes.
the Gaussian process on the finite domain transforms to just Gaussian distribution multidimensional.
So this is multidimensional Gaussian distribution, right? With a zero mean and something like this.
Mm-hmm.
which lives in the space C by C.
If we transform it to a vector, yes.
Yes.
Yes, like this, yes. So,
And this is exactly what is it here.
yes.
Good.
I am absolutely confused now. Can you summarize the result of
Can you
your
summarize the result?
discussion?
Because I think the notation was not too good. It was misleading. When you start telling that in both cases we're using Gaussian process. No, in the second case we're not using Gaussian process. We're actually using just multidimensional Gaussian variable.
First, is it correct that we trying to replace?
I think the easiest formula is written just here. So what is FB? We
Sorry, what is our purpose? What
I
do
don't
we
know.
want now?
You say that you're confused. With what
Yes.
you are confused?
With that slide, absolutely just from the start of that slide.
Just from the start?
Yeah.
Okay, you understand what is search prediction problem is?
Yes.
So do you understand this co-function which is at the bottom of the slide? It is the same co-function as written here.
Okay. Yeah.
So now we just use a probabilistic model for multi-class classification, and in this model we put our new score function instead of the old score function, this f.
Okay. Okay.
That is all.
And
But the table wasn't pairwise term. Because
yeah.
unity term is the same as the multi-class classification problem.
Yeah.
So it is clear. The Dale isn't in the second term.
I
Pairwise.
have one more stupid question. Now I know what is 1 and 2. What is I? I'm sorry.
Here, that's the number of
Like,
objects from
What
training
is
set.
X by PI? It's like-
XPI, it is a pixel number P from the image number I.
So YI is a
YI
label
segmentation.
Is a vector, is a segmentation for image number I.
So this is multidimensional variable. And its components are given by YPI. So its components are indexed
Yes.
by P.
Yes. So Y
Why then
lives
like
here in Y big, that's a
why there is
structure.
no I in the YP head?
Because Y hat is just one segmentation.
Oh, so it's some respect to
So
all the possible.
all possible, yes,
segmentations.
yes.
Oh my god.
And
Yes, similar to this maximization problem with respect to all possible segmentation, the summation with respect to all possible segmentation is a difficult term. But this is the standard problem, and there are a lot of approximate or even exact algorithms for efficient calculation of these things.
For example, this is partition function for CRF.
Yes, for instance, dynamic programming, if we have a chain,
But this is definitely not the case. Because for image segmentation you don't have chain.
or tree structured for images, tree structured approximation to this term.
Very inefficient and exact.
It doesn't matter to be a good approximation. We only need to have, well, good gradients in order to find good parameters, that's all. Okay, so that was about the basic heuristic models of Gaussian process for standard machine learning programs. So how are we going to learn this model? By learning, I mean to find the parameters of covariance function, theta, parameters of a noise if we use regression, and also the finding the hidden regression function for using on the prediction stage. Here our model, the simplest one, if we speak about regression or two-class classification. And this is just the standard probabilistic model with hidden variables. Y is observed variables, F, the value of our Gaussian process, is hidden variables, theta are some parameters, so we can learn this model using standard EM algorithm, or if you like, variational inference with evidence lower bound. So we put a log likelihood, lower bound it with a standard evidence lower bound, and maximize it with respect to both our parameter theta and our additional distribution Q over a set of hidden variables. And in ideal case, when we have an optimal theta and optimal Q of F, this Q of F should approximate the true posterior distribution of F given our training set. And what people usually do here, they use just a normal distribution with a general multidimensional distribution with some mu and sigma, and then maximize this function with respect to these parameters. Yes?
Why is a F hidden variable? I thought that it is our input.
No. Our input is X, that's the feature vectors, and also Y, that's a target variables from training set. That is what we know. And what we would like to understand is this hidden regression function for all training objects. And this is F.
I've lost your question. Can you go one slide? Yeah.
You like this
Where
one,
is
yes.
No. The question is about the next slide. I don't remember where is the theta here.
Theta stays here, and theta controls the covariance function. So here
So
is
the covariance
GP
function-
prior.
For unary potential.
Oh, only for unary potential. So
Yes, because in binary
without
potential we do not have parameters.
Okay.
Okay, so we solve this maximization problem with respect to theta and sigma, and on the testing case, since we have a Bayesian model, we do not use the point estimate for our F, but make an integration with respect to posterior distribution.
So for the case of regression problem, actually the inference is tractable, at least for small data sets. But if Y,
Inference is tractable everywhere.
if Y is are class labels, then inference is not tractable. And we have to approximate it.
You mean here there is it is not an exact value?
Yeah.
Yes, for classification it is not exact.
Oh,
Just an
clarify.
approximation. Yes. So what we have till now, we have these Gaussian process models with some training procedure. The good thing is that there are no parameters which should be tuned by user. Everything is learned. For instance, it is opposite to SVM struct when you use SVM for structure prediction, where you have a set of parameters, this penalty coefficient that you should tune somehow. If you use Gaussian process, there is no problem with this. And also, we have a distribution at the prediction stage. So, for instance, we can calculate the variance of our prediction, and this variance is sometimes important, for instance, in Bayesian optimization. But there are two problems with this model. The first one is that it costs cubically with respect to the size of the training set. This cost goes from this term. Here states some probability distribution over vector f, where f is a vector of the size n, of the size of the training set, and here the normal distribution with arbitrary covariance function of size n by n. And in order to just calculate this term, even unnormalized version of this term, we need to inverse this n by n matrix, so we come to n cube complexity, and this means that we can apply this model almost for all data sets, only for very small ones. So that is one thing, and the other thing is that if we apply our Gaussian process, for instance, for image segmentation, for NIST, CFAR, etc., we won't get good results because our initial features, our pixels of image are not good features, and the Gaussian process model itself is not able to reconstruct quite complex transformation, quite complex dependency comparable to neural network. So,
but that depends on parameterization of covariance function. If the family of covariance function is rich enough, then it is possible.
yes, I mean if we use something like square exponential or something. Yeah. So the important thing is to try to put a neural network or some similar thing within the training of Gaussian process in order to be able to work with standard images and things like that. So now let's try to cope with the problem of a cubic dependence on the size of the training set. Usually it is done with so-called inducing inputs approach, which we discuss now. Well, the main idea is actually shown here. So on the left picture, we have some training set, which are blue circles, and restore a full Gaussian regression from this training set. And now we may ask the following question. Is it possible to find a new training set with different positions, with different target labels, some training set which is shown here by red circles, in such a way that restoring the full GP model from this red sample coincide with the GP model trained from the blue data set? Is it possible? The answer is that if the number of points, number of red points is smaller than the number of blue points, that in general we can't get the exact restoration, but we could hope for approximate restoration. And here in this picture you see that the Gaussian process that was restored from red data set, its mean function almost coincides with the blue curve. The difference only in the variance, a small deterioration of variance exists. But anyway, the number of points here is much less than the number of points here, and we got almost the same result. That is what we're going to use. So we introduce so-called inducing inputs, some new training inputs, some new inputs, which we denote by Z. That is positions of these inputs, and U is the value of the Gaussian process at these inducing inputs. And their number is M. M is usually much smaller than the number of the size of the training sample. We choose it by ourselves, for instance, 100, some small number. And our assumption about this restoration is actually can be written like this, that the posterior distribution of our Gaussian process, if we know the value of the process at red points and the training set, is actually the same as if we predict our Gaussian process value using only U, using only positions, the value of the process at inducing inputs. So let's write down the particular formula that goes from these assumptions. So first start with so-called augmented model. We use our standard model and added these inducing inputs, these inputs Z and their values U, and introduced the similar model. So here the data likelihood as it was in previous model, and here's a joint Gaussian process on F and U at points X and Z. So at training points and at inducing inputs.
Does it assume that Z is fixed?
Z is fixed, yes. And if we look to this model and calculate from it the distribution of Y and F only, so come to the previous model by just integrating out our additional variables, we come to this exactly the same model that was before. So till now, consideration this augmented model doesn't introduce any approximation. That is exactly the same model that we used before. Then, if we want to train our augmented model as usual, so we write down the lower bound, evidence lower bound. Now we have two hidden variables f and u, and we need to introduce some variational distribution of them. Here they are our function. And in ideal case, our variational distribution should approximate the true posterior distribution of f and u given training set. And this posterior distribution always can be written as the posterior distribution of f given u and y times posterior distribution of u given y. And our assumptions say that this distribution can be written or can be approximated with a high quality with just the posterior distribution of f given u without knowing y. So that is how we actually chose our family for variational distribution q of f and u. So we put here this term, which should approximate with a good value this posterior distribution. And then we also need some term which would approximate this distribution over u, and we say that it is some distribution. And as it was before in the first model, we just put here a normal distribution with parameters mu and sigma. So that is our family, our variational family, where we are going to find and approximate posterior.
Excuse me, what was the motivation of omitting y in the first term? In the last line.
Now we will cut. The motivation was till now only on the picture that using this assumption we could move from training a GP on a large data set to training a GP on a red data set, which has much smaller objects, and that is why it is more simple. And now we come to the particular formulas that actually shows this, that this is exactly more easy. I write it down. So here, again, that is our family for looking for approximate posterior. That is the usual evidence lower bound in our model, and we just transforming this expression. Once again. So what is our problem with this criterion function? Our problem is with all terms that contains f. F is a huge vector of the n is a huge value, and we do not want to have any terms in the criterion that we want to maximize with this f in order to reduce the complexity. So let's just write down the values for the joint distribution and for our approximate. The joint distribution, we have the usual data likelihood. Then we have a joint Gaussian prior over f and u, and I can always write it as the conditional distribution of f given u, x, z, theta, and p of u given z, theta. That is the denominator, and in the denominator we have this thing. And as you see, this term cancels. And this is a cut term because it is a distribution of our n-dimensional vector. And using this assumption, it is possible to eliminate this cut term. But it is not enough. We again have f here, so we need to do something additional. Okay, let's continue. So I write, this is the first term and the second term. It's a sum of two terms. The second term is easy. This is the distribution over vectors u, and u is a small vector. It has a size of the number of inducing points that we chose by ourselves, like 100. So here are a low-dimensional distribution.
Moreover, it can be computed analytically, because this is scale divergence between two Gaussians.
Yes, yes. The problem only is here. And now we just put here that our likelihood is a product of separate training objects, and say that it is actually sum of training objects of what? Of a term that depends on f and u only through fi. So that is why this is expectation with respect to qfi. Minus chiral divergence between distribution of u and prime distribution of u. So what we see with this criterion function, I think it is written, yes, it is written here. So the first good thing is that our criterion function is actually sum of objects. So we can use stochastic optimization for this thing. The other thing is that this term can be computed analytically, because Q of u is a normal distribution, and this P of u is also normal distribution, and KL between two normal computed analytically. And so the last thing that we need to know is what is Q of fi. Okay, let's calculate this. That's again our criterion function. And first, if we calculate Q of f, just marginalizing u from Q of fu, put here our assumption on the variational distribution, that's the product of two terms. Here stay the predicted distribution of a Gaussian process. If we know the Gaussian process at points z, what would be the value of the Gaussian process at points x? So that is the standard normal distribution with some particular parameters. Here Q of u is again a Gaussian distribution with mu and sigma, and this is just a convolution of two Gaussians and calculated analytically. So that's a some Gaussian distribution with these parameters. This factor is hard to calculate because here stays KNN. KNN is a covariance between all pairs of training objects, so it's n by n matrix, huge matrix, and we can't deal with these objects. But we don't need to know Q of f. The only thing that we need to know is Q of fi for each independent object. And Q of fi, that's again a normal distribution certainly, but in order to calculate Q of fi, we just need to use a diagonal of this KNN, not the whole matrix. And some other parameters which has the size m by m without any m parameters. So this thing can be calculated efficiently. And that was already discussed, that divergence can be calculated analytically. And now let's estimate the total cost of calculating this criterion function with respect to m and n, number of training objects and number of inducing inputs. For calculating this thing, the cost is m cubed, because here we have a matrix m by m, m by m. So all matrices are m by m, and we need to invert them to calculate the determinant. So it's all m cubed algorithms. And as for Q of phi, here states a product of a matrix m by m times some vector of the size m. So here the m squared cost, and we need to do it for all I, for all training objects. So the total cost is n times m squared. And the total cost of all the criterion is just like this. So it's m cubed plus n m squared. The important thing is that with respect to n, we have a linear dependence, which is much better than n cube, and could possibly use this method for very large data sets. And also some minor issue on calculating this term. This is actually one-dimensional integral because y is just a value. So it is always possible to calculate a one-dimensional integral using quadratures. It's not a problem. But in case of regression, when we have here a quadratic function with respect to y, and we need to estimate an expectation with respect to normal distribution, it can be calculated just analytically, just a formula. And if we have a logistic function, in order to calculate this, we can use a reparameterization trick and to sample from standard one-dimensional normal distribution, and this sample can be used for all training objects. We don't need to sample it for each object independently. We can use this thing, or we can use a Gaussian quadrature. It also works very good because the integral is one-dimensional. Certainly, if we speak about structured prediction likelihood, it's not quite an easy thing, but there are a set of procedures for this. Yes?
Normal choice of M.
The normal choice of M?
Yeah.
The larger, the better. We'll come to this because, okay, let's summarize what we have from inducing inputs approach. We have a complexity of this kind, linear with respect to number of objects, and cubic with respect to number of inducing inputs. It means that we do not have ability to take a lot of inducing inputs, like 1,000 the maximum. Also, it is possible to maximize our criterion function with respect to position of inducing inputs. It is possible, but in practice, it requires too much time because there are a lot of parameters to optimize, and usually people just set some fixed z, for instance, as cluster centers of our training set. And there are two limitations of this model. The first one is that we can use here only a small number of inducing inputs. And actually, it is a problem, because if you think on what is inducing inputs, we have our training set in the multidimensional space in initial features. And this training set forms some low-dimensional manifold. And what we are doing with inducing inputs, we approximate this manifold with some lower number of points. If we live in a very high-dimensional space, we have a lot of features. It means that this low-dimensional manifold of training set would also have a rather high dimension. It means that in order to approximate it at a good quality, we need a lot of inducing inputs. 1,000 could be not enough. So, and indeed, and the empirical evaluation really shows this, that if you take machine learning problems with a lot of features, that inducing inputs approach shows not good results. So we want to somehow scale with the number of inducing inputs. That is one case, and the other thing, the problem that I said about the full GP model, that again we don't have here any neural nets, can't cope with image segmentation problems. Okay, let's start with adding a neural nets to our model. It can be done in a very straightforward thing. Just use a covariance function of this kind. So we use a neural net which gives us a good representation for our object. So here we take our images as input and transform it to some low-dimensional space, and then construct a Gaussian process on this low-dimensional space. Very easy model, but there is one problem with it. The problem is with position of inducing inputs. As I said before, it's a good choice to take cluster centers as position of inducing inputs. But when we learn all this model at once, it means that when we change the parameters of our network, we change all these x tilde, and it means that clusters are also changes. So we can't put the position of inducing inputs once and use them all the time. That is the problem that we need to solve here, and what we decided to do is to put inducing inputs at a regular grid. We use a sigmoid function, activation functions at the last layer of our network, so our output, all these x are between 0 and 1, and we put at this cube our inducing inputs at the multidimensional regular grid. That in this situation we don't need to change it on all iterations. We constantly cover all this space with our inducing inputs. However, if we do it in such a way,
I'm very sorry, but I still don't understand. The inputs are what? Are x-tiled or x? Because you are putting regular grid on x-tiled.
yes, here. So input is x. That image is here. Pixels of image is here. Then we transform it to some representation by neural networks, some low-dimensional representation, and then construct Gaussian process in this space.
So then the question is how to compute covariance function between given point on a regular grid x-tiled and a given image. So you may convert your given image to x-tiled space,
Yes.
right? And how to compute covariance function there? Simply radial basis function or something like that?
You calculate the function that you use here. If it is squared exponential, you calculate squared exponential.
And what do we use here? Squared exponential?
Yes, you use
Okay.
here squared exponential.
Okay, now I've got it.
Sorry,
Yes.
why cannot we feed centroids clusters and process them with the same network and use them as inducing inputs in a new space?
I don't understand what does mean process it with the same network. The cluster centers are here. So if we change parameters of the network, the cluster center completely changes.
So you mean centroids with respect to what? Centroids in the space of images? Or
Yes.
But
First of
centroids
all, it's not
here
clear.
do not correspond to centroids here.
Well,
Because of nonlinear dependency.
well, the transform is the same. No?
The transformation is nonlinear. This means that centroid in the space of x does not necessarily correspond to the centroid in the space of x-tiled.
Yes, I understand that they will be no longer centroids, but will it be a possible solution?
Well, you need to cover by your inducing inputs the place where your training set lives. If you put just arbitrary points, you won't get a good quality for approximating our posterior.
Yeah, but these are not arbitrary points. These are centroids. So if we take centroids in the space of images, we in some sense will get some representative set of images. And we may use only them. Or alternatively, when we convert all images to this x-tiled space and to find centroids there. In some sense, again, we'll get some representative set of
But we need to
our training
find
data in the space
these
of x-tiled.
centroids on each iteration,
We won't be able to train.
because we change the parameters of our network.
Right.
That is the problem.
Exactly.
It would be too hard to do.
And this is the answer to Pasha's question. Good.
Okay, so now if we put our inducing inputs on the points of a regular grid, the number of inducing inputs just scales exponentially. For instance, if we take like 10 points per each dimension, the number of inducing inputs is a 10 in the power of the number of dimension. So it's a huge number, and we need to to reinvent all the training procedure in order to work with such a huge number of inducing inputs, because the inducing inputs, the standard procedure works only for 1,000, not more.
And
So-
what dimension do you use in practice for neural networks?
You mean
D.
here?
Yeah.
I have the slide with the result of experiments. We will see. Okay, so now we are going to make a set of approximations in order to being able to work with this multidimensional grid of inducing inputs. So the first note is about Kronecker product between two matrices, just in order to remind you that if we have a Kronecker product of a matrix, it is easy to calculate the inversion and determinant of this matrix. So the inversion of Kronecker product is Kronecker product of inversions, and the determinant of Kronecker product is the product of determinant with a particular degree. So it's easy operation. And so now we put our inducing inputs on a regular grid, okay? And so here the notation that Mi is the number of inducing inputs per dimension, and M is the total number of inducing inputs, that's the exponential value. And now we may note that if our covariance function is not arbitrary, but it can be split over dimensions, so our covariance function can be written as a product of some functions over dimensions. This is what is actually we have for squared exponential case. And we take x and y on a regular grid. In this case, our matrix KMM, the covariance mass between all pairs of inducing inputs, is just a Kronecker product of covariance matrices constructed for each dimension independent. So, and this matrix is very small. If we take like 10 points per dimension, this is 10 by 10 matrix. It is very easy to do everything with this. And here the huge matrix M in M1 times M2 times MD, so this is a huge matrix. So covariance matrix for inducing inputs can be written as a Kronecker product of small matrices. Then we need to work with the covariance between inducing inputs and training inputs. Calculating this covariance, it is like calculating a similarity between some points and at points that put in a regular grid. That is a standard actually problem for in image processing when you want to calculate some similarity between some points of an image with points on an image put on a regular grid, and usually it is solved by different interpolation methods. So we first calculate the similarity or covariance between all pairs of points on this regular grid, and then reconstruct the covariance between a particular point with all inducing inputs by some interpolation functions of cross covariance function of inducing inputs. So here is the formula that this matrix can be written as cross covariance function between input points times some weight, and this weight is constructed in such a way that is also is a Kronecker product over dimension. So we have a point here. We consider over each dimension independently the 4 nearest neighbors and calculates weights for this. And the weights, the total weight is just a product of weights per each dimension. That's a particular way of interpolation, but it would be beneficial for us to have a representation of such a kind of these interpolation weights.
Well, you mentioned that this is known from computer vision community, right?
Yes.
But
They have a lot of methods for all regular structures. If you have a grid, if you have hexagonal grid. They have a particular efficient process.
Okay, but computer vision deals only with the two-dimensional and three-dimensional spaces, not with d-dimensional. So is it correct to generalize it to arbitrary dimensions?
Yes. Why not?
I don't know. Maybe they would justify it just for two and three-dimensional cases.
No. Okay, now return to our criterion function that we need to estimate efficiently. That formula goes from our interpolation idea, and then we just put, instead of k of I, this product. So we put it here and come to the scalar product between two vectors w and mu, and also put this here. And instead of matrix vector product, we just have here just a vector w, and here the KL term. So now what we have? We have that KMM is a Kronecker product of some small matrices. It means that this K inversion of K and calculating the determinant of K is easy. But we also have here some sigma. Sigma is a huge matrix. It has a size m times m, where m is the number of inducing inputs, which is exponential value. We also have this vector mu. Vector mu is also huge. It has the size of m, which is really big vector. We don't want to work with it directly. And this vector is easy to cope with because it is a Kronecker product of some vectors or dimensions. So we need to do some assumptions, additional assumptions from this sigma and on this mu in order to calculate all the necessary values here efficiently. And what we actually do here, for the vector mu, we use a tensor train format. What is vector mu? Vector mu is the mean of the value of our Gaussian process at inducing inputs. Inducing inputs are put into multidimensional grid. So this mean is actually a multidimensional tensor. That is why it is natural to try to approximate this multidimensional tensor with some tensor decomposition methods. And the most popular of them is Tensor Train decomposition. So that is what we use here. Now I think it doesn't matter the particular formulas here and how do we perform operations. It's just important to know that with Tensor Train format, we are able to store our multidimensional tensor efficiently, with not a lot of memory, and to do a lot of linear algebra operations that we need. Actually, that's all operations that we need here, like a product of some matrix which is Kronecker product over TT vector. That's an easy thing. And what else should we do with mu? And here, it is our vector W, which is a Kronecker product over dimension. It can be interpreted as a Tensor Train format. So this is a particular case of Tensor Train format where you have a rank equal to 1. So this operation is just a product of two vectors in Tensor Train format. So that is for mu, and as for sigma we need an operation of taking the determinant. And in order to estimate it efficiently, we decided to use also a Kronecker product over dimension similar to our covariance matrix KMM. So if we use this format, it's easy to calculate the determinant of sigma or inversion of sigma. And with these two assumptions, everything here is calculated easily with the following cost. So here M0 is the number of inducing inputs per dimension, so it's 10. And we see that the total cost is linear not only with respect to the number of training points, it is also linear with respect to dimension, to the number of features. So we can potentially use this method. We have a number of inducing inputs, M0 in the power of d, a huge number, but we never store any vectors of this size. We store only this TT cores and these sigma factors, works with them, and the total complexity is linear with respect to the dimension.
So, what is the upper limit for the dimension where the method is still applicable? Is it hundreds, thousands, millions?
Tens.
I will show you the, the experimental results. Here, the one more subtle thing exists. Potentially, we can use here rather large values. But we need to understand that what we do here, we are trying to reconstruct the values of Gaussian process at all inducing inputs. If we take here, for instance, m0 equals to 10 and d equals to 100, we have 10 in the power of 100 values that we actually restore from our training set. It means that in order to do this, well, with a good quality, you need to have a sample of the size similar to this 10 in the power of 100.
Dmitry, I'm not agree with you, because we are Bayesians, we have prior distribution. And actually we're computing here some estimate for the posterior distribution, which works even if we have training set of size, say, 10. In this case, we should be able to reconstruct some posterior distribution. And this means that even if we need to estimate the value of Gaussian process on a regular grid of size, say, 100 of 1,000 points, we may do it even if we have a training set of, say, 100. We're still able to do that, to do this.
But
of course, uncertainty will be high.
But the uncertainty, and also it could be.
We're still extracting some information.
Okay. So now we combine all this together. We put here regular grid, put a neural network as our pre-transformation, and it's important to know that we learn all the model simultaneously. We do not do any separate training of first our neural network, then GP, then combination. We just train all end-to-end. And some experiments. So the first experiment is very simple. If we take a digits data set, so it's a subset, a small subset from list, and if we try to draw, if we take here just 2 neurons and try to draw our sample in a two-dimensional space for this model, that is the result. We see that this two-dimensional space is not only good for making a classification. It is. It has some more properties that objects from the same class are mostly situated near to each other, and objects from different class, they are far from each other. It would not be the case if you don't use a GP here, but just use a normal neural network. Because for neural network, it's enough to reconstruct some space from which you can solve the classification problem. You don't need to divide your classes on different parts of the board. But for GP, it's because it works on covariance things in our space, it's important that objects from one class should have high covariance and objects from different class should have low covariance.
GPs, at least in the case when you're using this radial basis function, is in some sense analog of k-nearest neighbors. This is why it tries to form this compact set of points for the objects from the same class. And neural network, it constructs the inner representation on the last layer in such a way that if we apply softmax after this, we'll get high accuracy.
Yes.
What does it mean geometrically?
It will be nothing. We can't predict the particular view.
The point should be in some sense linearly separable.
Linear separable, yes. Yes.
So, but this is still important. So the picture will be different, but it will still have geometric interpretation.
But you actually can change the loss function for a neural network and do it like a covariance between objects in one class. It will work like this.
Okay, yes, maybe.
I mean, I tried it. It worked at least.
Okay, now this some slides with numbers. So here is just experiments without neural networks, and here experiments with neural networks. And this approach is called TGP, and here we compare the TGP with a standard inducing inputs approach for regression and for classification. And as you see that for almost for all these problems, the accuracy for the TGP is higher than the corresponding accuracy for inducing inputs approach, and you see here the number of inducing inputs that were actually used. Like here, 12 in the power of 10. So there is a much higher number than here, the number of inducing inputs. It is not so easy to compare this method directly, because here we put inducing inputs on a regular grid, and here we put inducing inputs at some points of our space. But
in some sense, in a smarter way.
in a smarter way, yes. We could actually here clusterize our training sample. But anyway, we see that we have some benefits in terms of accuracy and also in terms of time. If you compare the time per one epoch of stochastic optimization, you see that this method was quicker. And that's some very preliminary results on using neural networks. And what we can say here is here is some other approach of trying to incorporate neural networks into Gaussian process model. Here is just a neural network, and here the TGP. And what we can say is that if we want just to solve our classification problem on images, the neural network works good. There is no reason to consider the TGP here. But the interesting thing is that the time for TGP is not much higher than the training time for DNN. So all this machinery with GP doesn't require a lot of computation comparing to the computation of DNN itself.
And what was the structure of internal neural network into TGP? Was it the same as in...
Yes, this is the same structure is used here. And if we compare this with this, we can say that, for instance, on C5 we get a huge improvement over previous work with GP with neural network. Okay, that's all that I wanted to discuss today.
Do you somehow ensure that the outputs of the neural network lie in some range, like from 0 to 1? Do you have sigmoid in the end of the
Yes. Because we need to put our regular grid at some particular position. So we use the sigmoid at the
But in
last
this
level.
case, you would probably get that many points fall somewhere near 0 and 1, and so you should probably have denser grid near the boundaries of your cube.
Yes, but we learn the neural network. So we learn the neural network not to predict the class label, but to produce a good points in this hidden space. So after learning, we will get something more like this, and not the points that are on the borders.
Why not?
Because otherwise it wouldn't provide good classification accuracy.
No, but if we still keep the clusters, then why not? So we'll keep the clusters, but the points will be more scattered, and there will be many points on the borders. So what? I mean, is there any reasonable explanation of why can't we obtain points on the borders? Because currently I do not see why not.
Because it is more complicated and unstable configuration.
Oh really?
I said that it is more
Because
stable.
there's a sigmoid
Yeah.
on the last layer, and it's quite unlikely that we could get large values as inputs to sigmoid.
Well, I think that it would be worth to draw actually the pictures and just to see. But I think that the situation would be something like this.
Okay. Any more questions? Oh, there are no questions. I should say I have, well, some feeling that the tool is great, but you're not using them. You're not using it in the right way. So you're trying to use it for solving classification problem that is already solved well, quite nicely, and you can't beat well state-of-the-art deep neural networks. Maybe
No, we
you
are
use it
trying
for
to-
different purposes.
We are trying to learn the representation.
So
And,
what? Who cares about representation? Everybody is happy with the current representations which we obtained from the last layer of DNN. So it's not bad.
Well, we hope that we will be able to solve a structure prediction problem with a much higher accuracy than SVM structure.
This is very reasonable, so you should definitely try it. Another possible option, if you tell that there is a chance that you learn better representation, right? Then you should find an application which uses just learned representations for some different purposes. For example, we have many applications in Yandex where the people are using the activations from the last layer for different purposes. So they have classification network, but they do not want to classify images. They only want to obtain, in some sense, informative representations from the last layer, which are used, for example, for image search.
Yes.
So maybe
For
for
several
such kinds of
problems.
applications, this way of building representations will be better. So again,
Different loss function.
well, Katya, you'll be one of our next speakers, so please present your ideas. Why not? Maybe this way is competitive, right? Why not? I'll tell you what. I would say that maybe it's better to try solving some regression problems using GPs. Because DNNs are not too good for regression. And GPs were actually invented for regression problems. So they were, well, somehow modified for classification problems, but they were also hacks. So actually, GP is a method for solving regression problems. And we have many problems where regression solving regression in a large dimension space is necessary. So this probably is what I'm going to discuss with you in PAP today. So okay, now let us thank the speaker.